Hello everyone. Welcome to this week's ECEGSA academic seminar. My name is Yuntao Liu, and I am also a vice president of ECEGSA. So if you come here often, you will see that I am the guy who is videotaping every speaker every week. So I feel very honored to stand here and give a talk today. I'm a second-year PhD student, and I'm currently working with Dr. Srivastava in the field of computer engineering. Today, I will talk about some ongoing research, which is about the attacks on some hardware security primitive called physical unclonable functions. Okay. First, what is a physical unclonable function, or in short, PUF? Well, it is a piece of circuit that is usually integrated in some ICs that utilizes the manufacturing variation of devices, and so that manufacturing variation gives this piece of circuit a very unique signature, and it is impractical to have exactly the same copy with the same signature onto another circuit. So in general, it's unique, and it can be used for functions like secret key generation or low-cost authentication. Okay. And in a generic way, we can classify the PUFs into two categories. One is the weak PUF, and the other is called strong PUF. Well, the weak PUF is called weak because it has only a very small number, or specifically, the number should be polynomial with the number of its possible challenge vectors or challenge bits. So the CRP here means the challenge response pair. Namely, you can give this piece of circuit a challenge bit or challenge vector, and it will give you a response. The challenge vector or challenge bit associated with that response is called a challenge response pair. Well, for the weak PUFs, as the number of CRPs is polynomial, so that is a relatively small number, you have to keep these CRPs in a secret. And as it must be kept secret, the limitation of its application is also kind of obvious, and it is just suitable for some secret key derivation process. And the examples for weak PUFs are SRAM PUFs and ring oscillator PUFs. We will see a little detail about this in the next slide. And about the strong PUFs, in contrary with the weak PUFs, it has a large number of challenge response pairs. A large number means exponential. Okay. Maybe we can have a challenge, the bit length of the challenge vector, maybe n. We can have something like 2 to the n challenge response pairs. And so, because the number is so large, maybe we can just use one CRP at one time, and that will maybe fulfill the whole lifetime of that device. So these CRPs can be public, and that will significantly reduce the cost. So it is suitable for low-cost authentication. And the examples for strong PUFs are arbiter puffs and some variations of arbiter puffs, so we call it the arbiter puff family. And also a novel idea of the Memristor crossbar puff. Actually, the Memristor puff is where I got my whole attacking idea from, and we will talk about it later. So first, the weak puffs. Well, first, the SRAM puff. The SRAM is just the same as the SRAM cell that we often hear about. If we just power on the SRAM cell and do not write anything in it, the manufacturing variation will give it the inclination about having a 0 or having a 1 initially. And that is random. So we can use this kind of feature to make it a puff. So if we have n SRAM cells in that puff, the number of CRPs is just n, because if we select a cell, it will tell us whether it is 0 or 1, and that the number of cells is just the number of CRPs. Well, for ring oscillator puff, it's a little better. The ring oscillator puff is basically, well, you have a set of ring oscillators, and due to some manufacturing variation, the ring oscillators are just like a chain of odd number of inverters while you connect it in a ring, so it oscillates. Due to some manufacturing variation, each ring oscillator will have a slightly different frequency, and so if you choose a pair of ring oscillators, you will have a comparison about their frequency. And so let's say if the first one, the frequency is higher, then you will get an output of 1. And on the other hand, if the first one is slower than the second one, you will get a response of 0, something like that. Okay. So basically we have like n choose 2, the number of n choose 2 many channel response pairs possible. However, there is such kind of thing that if like ring oscillator A is faster than B, and B is faster than C, so we know that A is faster than C. So essentially, like the effective CRPs is less than n choose 2. Actually, we can think of it in this way. If we have n oscillators, right, and the number of possible CRPs should be just like the ordering, the possible orderings, that is n factorial, right? And if we represent that in bits, it's just log the n factorial, and that is essentially the order of n log n. Okay. Okay, then let's talk about the so-called strong puffs. First, we have the arbiter puff family and the Memristor crossbar puff. Actually, the first idea of puff in the world may be inspired by this like kind of arbiter chains. Not arbiter chains, but like the max multiplexer chains. From this arbiter puff architecture, well, first, this is a latch. You often see this in some digital circuits, but here it acts as an arbiter. Well, the arbiter decides which of its two inputs comes first. I mean, initially, both D and this clock may be 0. So what does this latch do? When there is a positive edge of the clock, the inputs from D will be transmitted to the output Q, right? Well, we can just ignore all the setup and hold times for now, and that is the basic functionality of this latch. So in this puff situation, where we may have like a step signal at first, and after all these multiplexers, this initial step function will be transmitted to both the upper and the lower side of this latch. And let's say if this clock comes first, while this D is still 0, the thing that will be transmitted to the Q is a 0. But if the D comes first and the clock comes later, then the 1 will be transmitted to Q. And this is a basic idea about how this path works.
Question?
Okay.
What happens when they come simultaneously to that?
Well, that will depend on the arbiter itself. I mean, it's just like if you don't have enough, like if your D signal is not set up like in enough advance earlier than this clock signal, then what will happen to your latch? You can just think of it in that kind of.
So can you guarantee that the output Y is stable? We do not always guarantee that the output Y is stable, and that is kind of a problem associated with this kind of puff. Because, although I'm just studying about the techno puffs, but the puff itself has some issues like the puff has some intra-puff variance. We want this variance to be 0 because we want the challenge. We want the same response for the same challenge every time the puff functions. However, sometimes, maybe these two signals come too close, and this output can be dependent on some other variations like temperature, and that makes the puff behavior a little unpredictable. And that is not desired, but it's not within the scope of this study. So that's conservative. And by the way, as long as we want to minimize the intra-puff variation, we want to maximize the inter-puff variation. That is, we want maybe the puff like with the same architecture. Maybe we manufactured all these puffs on the same die, but we want the response of the CRPs among all the puffs to be as independent as possible. So that is also a metric of the puff functionality. The XOR arbiter puff is like a variation of the arbiter puff that I just talked about. Here we have multiple arbiter puff circuit, and their output comes into a XOR gate, and the XOR gate and the output of the XOR gate is the final output of the puff. A good thing about the XOR is that it destroys the linearity from the arbiter puff, because in the arbiter puff, all the delays on each stage is linear additive. That means the delay on the final stage here is just the delay of each stage added together, and that makes the attack much easier. Actually, later on we will see I formulated the Memristor Puff also into this linear additive way, and then formulated such attack and then extended onto the arbiter puff. But that kind of approach is not able to extend to this XOR arbiter puff or this feed-forward arbiter puff, because in either ways the linearity does not exist anymore, and we need to use other approaches. Another example, this is called a feed-forward arbiter puff, which looks very similar to the arbiter puff, except that there is a feed-forward arbiter inside the puff architecture, and it's like, this arbiter decides which one is faster at this point, and its output is fed into another multiplexer somewhere later in the puff chain, and that is equivalent. It looks like, equivalent to another bit of challenge vector, but we do not know that.
The lightweight puff it also shares many similarities with the former puffs. Well, what's special about it is mainly this input network. Well, for the these input networks are designed so that if we change one bit in the challenge vector, the output of the puff will change with the probability of 0.5. Well, it can be proved that in like the arbiter puff, the probability that the output will change is dependent on the position where the challenge vector, where the bit in the challenge vector is changed. So it's a function of its like index in that vector, and it's not always equal to 0.5.
So you implement the scrambles in the output network. That's the function, right?
Yeah, this output network is XOR.
No, I mean the block.
Yeah. This input network is kind of a scramble.
Okay.
Yeah.
Also the output network.
The output network is basically just of XOR.
So you just scramble the inputs with the input net.
Yeah.
Okay. The input, you mean the challenge, right?
Yeah, the challenge vectors. Well, then I will talk about something about the Memristor puff. But before that, let me just briefly introduce what is a Memristor. Well, this device was predicted to be existent in 1971, but no one has fabricated it until 2008. It is called the fourth basic circuit element, and namely the first three are just resistors, capacitors, and inductors. And let's see how this device works. Well, this is like a very simplistic intersection of the device, where on both sides we have a metal electrode, and inside there is some metal dioxide, where on one side it is doped with oxygen deficiencies. So this part is more conductive than that part. And when electric field is applied on this device, this oxygen deficiencies or other carriers inside that device will drift due to that like external electric field. And if the external electric field is forward, then the dopant will move forward, and ultimately the whole region becomes doped, and the memristor comes to its low memristor state, where the memristor is namely just the resistance of the memristor. Or if the electric field is backward, ultimately the dopant will shrink to one side, and the memristor comes into its high resistance state. Or when the resistance is low, we can also call it R on, and when the resistance is too high, we can also call it R off. Okay. So there are some interesting characteristics about this memristor. Here, the blue curve is like the voltage, and also the blue curve is the voltage, and the green curve here is like the current. Okay. So we see when the voltage is higher, I mean, as long as this memristor does not come to either limit of its memristance, the memristance of this memristor will go down, and
this graph shows, the lower part shows the change of W, namely the change of the width of the doped region is shown here. So when we apply a positive electric field, then the memristor will go down because of the increase of the length of the doped region. And so the current will go up. And interesting is that when our voltage go down from its highest point, the current will still go up a little bit, just because the memristor is going down. Even if the voltage has begun going down, as long as it's positive, the memristor is still going down. So the quotient of the voltage and memristor is still going up, and we can see kind of a delay in the current. And the same story happens when the voltage is negative and it's just symmetric. And here, this is, well, we see that the first 3 peaks are all positive. So from 0 times 0 to the middle, the memristor is always going down as the W always increases. So you see the current trace, it becomes higher and higher each time because of the memristor change. Okay. And by the way, that is what we say the memristor is non-volatile, which means even if you cut off the power, the memristor does not change back to its original states, but it stays in the state where you have last modified its memristor. And let me briefly introduce the memristor model that is used in such kind of Memristor Puff. Because it's multiple memristor processes or materials have been proposed, and those who have very sharp changes between their high resistance state and low resistance state is more suitable for our digital circuit applications. And somebody named McDonald did some experiment and proposed just this memristor model. Like first, in experiment, we figure out that there is kind of a threshold voltage where below this voltage the memristor does not change very significantly, or the change is negligible. But beyond that voltage, it changes very, very rapidly. So there is a clear transition between the high resistance state and low resistance state, but a very short transition. And that is the desire for the digital circuits. And in his model, he argues that, so I found that the memristor will change linearly with time, and this Ti and Ti plus 1 is just like 2 time junctions, and the delta T is time interval. This delta R is the difference between its high resistance and low resistance state. And Tp and Vp are associated with the memristor itself, where the Vp and Vn are the threshold voltages on the positive and negative sides, and this Tp the time needed for the whole transition under some unit voltage. And here comes the path that we would attack. Okay. Actually, we did much derivations on this path, but the basic idea is that initially, all the memristors in this circuit is initialized to its high resistance state. And